Greetings, Physics 3310 students. Hope you're all doing well. Hope you can hear me. Can someone give an indication that they can hear me? Thank you, Noah.
I can hear you.
Wonderful. Okay, we're going to zoom in a little bit here. For attendance today, please tell me, what is your comfort food? It's very important to have a comfort food. Right. So I didn't mean to lie to you last time. I said I was going to post a digital lecture and I didn't. It's still going to happen. I promise. We'll be providing you all of the contact hours that you deserve, that you have, signed up for. So that will be happening at some point soon, and I will let you know when it's ready. As a reminder, I did post the midterm grades, and I sent you feedback files regarding your midterms. So please take a look at those if you have not yet. And do we have any questions about that or feedback about that so far? Okay. Cool. All right, so let's check some upcoming deadlines in the class. So this week, we have our linear least squares. Sorry. This week, we have our correlation and covariance homework due on Thursday by 4 p.m. We have definitely finished talking about correlation and covariance as far as the strategies. We need to tie up some loose ends there today. But hopefully you've had no trouble getting started with that. And next week, your homework 9 will be due on binomial and Poisson distributions. So we're covering binomial today and Poisson on Thursday. Still need to do a little more adjusting of concepts here. Questions about any of that? Check. Can't see my midterm exam grade. Okay. If you can't see your midterm exam grade, email me. That is a little weird. Is there anybody else who can't see their midterm exam grade? Maybe it's just one person. Okay. Email me about that, please. Okay, so where did we leave off last time? Or do we have any questions? Yours, we do not have questions. Let me remind you what we were talking about last time. We were asking this question: if we have this plot of randomness, seeming randomness, where we have a plot that shows some sort of experimental outcome, that shows the change in variable B with variable A, or whatever variables we've decided on. If we see this sort of trend, like at the bottom right of the set of plots, it looks like there's a high likelihood of there being a linear dependence there. But there are some plots here where there may be some linear dependence, and we can't really tell. There may be some dependence of variable 1 on variable 2, but we can't really tell. So last time we quantified how to, or we described how to quantify that dependence with this idea of covariance. Okay, so as a reminder, we also use that quantity to define this linear correlation coefficient, R, which is defined as the covariance sigma sub xy divided by the individual standard deviations of x and y, the product of the two. And this number R is going to be somewhere between -1 and 1. You just take the absolute value of it if it's negative and think of it as a number between 0 and 1 that tells you how correlated those two quantities are. The closer R is, the closer the absolute value R is to 1, the better your points are fitting with a straight line, and the more linearly correlated they are. The closer R is to 0, the less correlated they are. Let's look back at this plot. There are correlation values shown here. Sorry, R values are shown here. For this plot up here, where things look quite random and there's not a whole lot of evidence of correlation, we get a correlation coefficient of 0.1. So quite close to 0 for that group of points. In the middle here, we have what looks like it might be a linear correlation, maybe, maybe not. It looks more likely than the one above or at the top left. And the correlation for that one is 0.5. So, you know, kind of a 50-50 chance that those are linearly correlated. If we look at the bottom right, our correlation is 0.9, meaning it's a 90% chance those two factors, those two variables are correlated with each other. So that's what that linear correlation coefficient R tells us about our data. Okay, then to remind you, we did an example problem in breakout rooms. This was it here. And the question was to find the linear correlation coefficient R for the data given. Okay, so we were given counties in North Carolina, percents of voters in those counties that voted for Obama in 2012, and then percents of people in those counties with college degrees. So the idea was to see, are these two sets of data correlated with each other or not? And so in part A, we found the linear correlation coefficient R for the data given. Okay, so this is where we left off last time. And I did check my math, and I believe we all got the same answer here for the values that were calculated. So here's the given data again. The percentage voting for Obama, the percentage with college education. Those are copied here in columns B and C on my Excel spreadsheet. And then we are calculating this quantity R for the given data. Okay, so with what was given, first what was found was this quantity x sub I minus x bar here in this column, x sub I minus x bar. So x bar was found just by averaging the values in column B, which is our x variable, And then y bar was also found here by averaging the numbers in column C, which is our y variable. So here we took each row of column B and subtracted the average. And here in this column, we take each value of y and subtract the average, and that's this column. So we're building the numerator and the denominator, building the pieces. Okay, then we took, supposed to say DE, sorry. We took column D and we took column E and multiplied those together, and that's this column here. Okay, so we just took this number and multiplied by that, and that's that. Took this number and multiplied by that, and that's that. Then we also took D, each of these quantities, and squared them to get this quantity here. And we took each of the yi minus y average values and squared those in column H here. And then we wanted to add those up in the numerator and add them up in the denominator and take the square root. And so that's what this this quantity is here. Our final quantity there is R equals the sum of the things in the numerator divided by the square root of the sum of the things in the denominator. So we end up with 0.935. We go to our chart. And we choose n is equal to 1, 2, 3, 4, 5. We choose n equal 5 and r at about 0.9, and that gives us a 3.7% chance that these variables are not correlated with each other. Just to remind you, that's what's listed there is the values that the two quantities are not correlated. So there is a 97.3% chance that these two variables are correlated with each other. In this case, in this particular set of data. So the point of doing this example is to realize that we need to be careful. I'll get to that slide here. We need to be careful and realize that correlation and causality are not the same thing. If we have evidence that there are correlations of variables, that means in the future, there's probably going to be more correlation of those things. But it does not mean every single time we consider one of those variables that the other one will correlate every single time. So we have to be careful and realize correlation does not prove causality, and we need to, pay attention when those in the media or those in advertising or politics use statistics and use probabilities in ways that they shouldn't, in ways to confuse people and to deceive people. So while we can say with great certainty that there is a correlation between those who voted for Obama and those who had a college education in these counties in North Carolina in 2012, it does not mean that every single person with a college education voted for Obama. It is not the same thing. Okay. We also need to be careful about looking silly when we're using this statistic R. In this case, with North Carolina counties and voters and college education, we really didn't know for sure ahead of time if there was a linear correlation here or not. If we're considering the relationship between the speed of light and the frequency of the light and the wavelength of light, then we're going to expect a linear correlation. or the speed of light with respect to some distance traveled and the amount of time it took. We know there's a linear correlation there. So if we throw up some speed of light data on a plot and find the R value, it doesn't matter. We don't care. We already know it's linear. So the value of R in that case is really not that helpful. It's not really useful, and since we already know that's linear. We're not trying to figure out if those two variables are correlated or not in senior seminar. Okay, do we have questions? Comments? Feedback? Have you been deceived by probabilities in the past? I hope not. Okay. Speaking of probabilities, we're going to move forward and maybe be reviewing for some of you, or maybe be learning some things for the first time. But we're going to talk about statistics. So basically, we are going to be talking about predicting the outcomes of situations based on the physical properties of those situations, or of those of the variables involved. So some of you may have not had this before. Some of you may have had this, seen this in thermal physics or in a statistics class. If you haven't seen it, that's okay. And most of these classes use the same kind of introductory examples for learning about determining the probabilities of outcomes of processes. We like to use flipping coins and decks of cards. So we'll be doing that. And if it's thermal physics, then you have quantum particles and states. We're going to start with simple game-like examples first, like our sister classes. So let's consider a situation where we're going to have a whole bunch of independent events that are equally likely to occur. If we wanted to determine the probability of those events happening, we would add up the total number of possible outcomes, add up the total number of ways to get whatever our desired outcome is, and then divide the two. So let's, for example, say we have playing cards. There's 52 playing cards. Each card is different. Let's say we want to find the probability of drawing a jack out of the 52 cards. Well, there's 4 jacks and there's 52 cards. So there's 4. The probability I'm going to draw a jack is 4 out of 52. If everything's truly, if all of their factors are taken into account. If it's truly like a random draw. If I want to determine the probability of drawing a face card, a jack or a queen or a king or an ace, I guess an ace isn't a face card, a jack or a queen or a king or an ace, well, there's 16 ways to do that. 16 possible cards to draw out of the 52 cards. Okay, not counting like if it's a certain suit. All right, now let's think of something a little more complicated. We have a set of 2 dice. So we're not just pulling one card now out of a deck. We are taking 2 dice and rolling them together. So we have 2 possible outcomes, or 2 possible like face values once we roll those dice. There are 36 possible outcomes if you roll a pair of dice, because there's 6 sides, and each side has 1, 2, 3, 4, 5, or 6 on it. So I could roll a 1 and a 1 and get a 2. I could roll a 2 and a 2 and get a 4. I could roll a 4 and a 1 and get a 5, etc., etc. So here's all the different outcomes. And what is shown in the along the top and the left is like the face values of the dice, and then the sum of the two values is shown in the grid here. So the most likely outcome is rolling a 7, a total of 7. Why is that true? Why is that the most likely one? That's because there's more ways to roll a 7 than any other way to roll something else. There are 6 ways to roll a 7. 1, 2, 3, 4, 5, 6. 6 ways to do that. So that means I'm going to roll 7s most of the time, because that's just the most, there's just more of that possible to happen in the first place. So that's a probability of 6 ways to roll the dice to get a 7 out of 36 total outcomes, which is a probability of 1/6 to roll a 7. The least likely outcomes are to roll a 2 or a 12. There's only one way to roll a 12. There's only one way to roll a 2. So those each have a probability of 1 out of 36 of occurring. And again, that they are going to occur much less often because there's just less ways for them to occur. That's why. Okay. Now, what if we repeat actions and then want to find out the probabilities? We're repeating the same actions over and over. If we are rolling the dice over and over and over, the set of dice, the pair of dice, over and over and over, then the final total probability is going to be equal to the product of the individual probabilities. So let's say we have a coin. We flip it 4 times. Each time we flip it, each individual time we flip it, there's a 50-50 chance of getting a head or a tails. Head or a tail. But if we flip it 4 times, the probability of getting a particular sequence of those halves of those events in together is going to be a 1/2 to the 4th. So that's for getting any particular sequence, not for getting one particular sequence. So let me elaborate. We have that coin that we are flipping 4 times in a row. We know that it's very unlikely to get all 4 heads or all 4 tails. But then we just said the probability of getting any sequence would be 1/2 to the 4th, or 1/16. How does that work? Well, let's look at all the ways to flip the coin. We're going to flip it 4 times. There's this many possible ways to do that, this many possible outcomes. We can have all heads, we could have all tails, we could have 3 heads and 1 tail, which is shown up here. We could have 3 tails and 1 head, which is shown here. Or we could have 2 heads and 2 tails, which is shown in blue. So there's 16 total possible outcomes for flipping the coin 4 times. And 1/16 of those 16 is when I have 4 heads. And then 6 out of the 16 times is when I get 2 heads and 2 tails at the same time. So it is much more likely to get 2 heads and 2 tails than it is to get 4 heads. But for any particular sequence, no matter what the sequence is, the probability is 1/16. Okay, now what if we start to care about order of things? We haven't talked about that yet. We just said, are there two heads? Are there two tails? That's all. We don't care if it's like tail, head, 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 tail, tail, whatever. We didn't care about order. Now we're saying, what if we take a situation like flipping coins or pulling cards, and now the order of the card pulling or the order of the results is going to matter. What if we want to know how many different ways there are to order things? Let's say we have blocks, BCT, and we want to line them up in different ways. Here's the different ways to line up those blocks in different orders. There are 6 different ways for our 3 different blocks. Notice they're not none of these blocks are the same. We don't have 2 B's and 1 T. We have 3 unique blocks, which means there's 6 ways to arrange those 3 unique blocks, which happens to be 3 factorial. It turns out for any number of objects, where the number of objects is capital N, the ways to order those objects is n factorial, assuming they are objects we can distinguish between, which starts to matter in thermal physics. If you can't distinguish between the particles, it doesn't matter. But if you can distinguish between them, it does, this ordering. So assuming we can distinguish, and here we could, B, C, and T, we can distinguish between, there's going to be n factorial numbers of ways to order those objects. Okay, we're getting to a point soon where we're going to have a formula that we're going to follow to be able to predict some outcomes, where those outcomes are ordered and or repeated. Okay, so first we need to understand this combinatorial function. Let's use this example to illustrate what a combinatorial function is. Let's say we're drawing pieces of paper out of a hat for winning a prize. There are 3 prizes that are the same. There's 100 people who have put in a piece of paper into the hat for the drawing. How many different combinations are there? How many different outcomes are possible here for people winning prizes? We don't really care about order in this case because the prizes are the same. We can't distinguish between the prizes. So there's no such thing as order because they're all the same. Like we can rearrange them and it's the same, however we rearrange them. So order we're not going to worry about, but we can determine how many different combinations there are of people winning prizes with this combinatorial function. So we take the number of people, the number of total ways for the total number of people in the pool, the total number of pieces of paper in the hat, and we take that factorial in the numerator. Then we take the number of winners. That's 3. The number of possible ways to win, or number of pieces of paper you're going to pull out of that hat, and take that factorial. And then we take the difference between the total number of people, total number of pieces of paper in the pool minus the number of winners, factorial. So this is the number of winners, like factorial, times the number of non-winners, factorial, and we take that product and divide the total number of people overall and divide by that denominator. So this is similar to our very first example where we were considering the total number of possible outcomes and then dividing by the total number of ways to get the different outcomes. So in this case, that's 100 factorial divided by 3 factorial divided by 97 factorial, which is 161,700. That's the number of different ways there are for people to win prizes. The probability of winning a prize is 3%. If you are one person, you might be able to, you have a small chance of winning a prize, which is based on the fact that there's 3 equal prizes and 100 people in the running. Okay, now, if we combine the idea of the combinatorial function with the idea of things being in order or not, with the idea of determining the probability of an outcome, we can finally reach this idea of the binomial distribution. So let's say we have a bunch of repeated events, and there's n trials. There are n different events, little n. And each event can have a different outcome. The one we care about is the one we will call the success outcome, the one we're interested in. Let's let P be the probability of the success of that outcome happening. So the likelihood of that event compared to the total number of events. And then Q is going to be the probability of failure, or just success not happening. The probability of success not happening is going to be 100% minus P, or 1 minus P. So to calculate the probability of B possible successes in n trials, we're going to use this binomial function, which is kind of a conglomeration of the past 3 ideas that we put together. Okay, so let's do some examples. What's the probability of getting 2 heads in 4 flips of a coin? Okay, so I'm going to be resizing things here so we can see this last slide as well. It has our formula. Okay, so again, P is the probability of success. U is 1 minus P is the probability of failure, and N is the number of trials. Okay, so I'm going to put the formula is over here on the left, and the filled in information is over here on the right. So what's the probability of getting 2 heads in 4 flips of a coin? Okay, so we have 4 flips of a coin, so that's going to be n. So we substitute 4 for n everywhere in our formula here. And then the probability of success is the probability of getting 2 heads. So that's going to be P. So P is the probability of getting 2 heads and 4 flips of a coin. So that's basically 1/2. 2 divided by 4 is 1/2. And then in that case, if P is equal to 1/2, then Q is also equal to 1/2. So we substitute 1/2 for Q, 1/2 for P, 4 for N, and we're trying to get 2 successes in our N trials. So V is also equal to 2. When we simplify, we end up with 3/8. This is the probability of getting 2 heads in 4 flips of a coin using the binomial distribution. This is the same that we calculated a few slides ago. We didn't. 2 heads and 4 flips of a coin. Yeah. So this was the same as what we got before, 6/16. But now we just used a formula to get us the same result. Okay, so that's our first example of binomial distribution function. Do we have questions? Okay. I'm going to put the question in the chat and send you off to breakout rooms. And you're going to be using that binomial distribution function to answer this question. Or you can use other things, but I would recommend using the binomial distribution function to answer the question. Okay, so putting the question in the chat. This is 10.10 from your book. And I will open up breakout rooms and put you in there. Okay, you should be able to go. Here we go. Okay, so did we get a probability that none of the patients survive? That was part A. Right?
I got roughly 41%.
Me too. Excellent. Okay, what about the probability of one patient surviving?
I got 2.56%.
I didn't get that. Anybody else get a different answer? I could be wrong.
About 10%.
10%? I got the same as part A, 41%. But I might have a typo. Might have an issue. Anybody else get 41% for B? I see someone nodding. Okay. All right. Well, definitely we agree on A. I will check my math on B. I'm trying to do these at the same time as y'all to like see if the timing's working out. And then for C, did we get anybody get a probability that 2 or more survives?
Maybe nobody got to that point.
I don't know if this is.
I was working on it when the breakout rooms closed. I was the only.
Yeah, it includes the results of part A and part B. So we're all going to have different answers anyway, probably. I ended up with 0.18, 18%.
Yeah, I also got that just now.
Cool. Awesome. Thanks, Jess. Okay. So I'll put this out on, with all the steps showing so we can compare and make sure we're all correct. And I'll post that on the As You Learn page. And we're going to have to stop now. We'll have more breakout rooms next time and talk about Poisson distributions. So have a great week. See you Thursday.
Also, I wanted to